Alright, so this is a video lecture of the information that we are covering in class during period 1-2 on Friday, December 21st. This goes with your 3.6 packet, so make sure that you are filling in the information as you watch this video. Feel free to pause or rewind it as you need because you'll be using that to complete the practice problems in this packet. So your essential question is, what is the difference between a chemical reaction and a chemical equation? Hopefully you remember the lab we did earlier in the year where you went around the room, you did a series of mini experiments, and you had to figure out if it was a chemical change or a physical change. So whenever you notice a chemical change, so that was things like temperature change, color change, precipitate forming, those are all examples of chemical reactions. A chemical equation is just how we communicate a chemical reaction. So it's a shorthand way of writing it. We use symbols and chemical formulas, and it shows us that the reactants on the left side are producing the products which are on the right side of the arrow. So this is an example of a chemical equation. These guys here are the reactants, so we have nickel 2 chloride and sodium hydroxide. And then the products on the right, we have nickel 2 hydroxide and sodium chloride. So that might kind of look like a lot to write, but believe me, it's way easier than writing out nickel 2 chloride dissolved in water plus sodium hydroxide dissolved in water produces solid nickel 2 hydroxide plus sodium chloride dissolved in water. It would take us a lot of time to essentially write this paragraph every time we studied a chemical reaction. So this chemical equation up here at the top, that's going to be what we're learning about today and how to write those. So these are the most common symbols that you will see in chemical equations. The arrow just separates the reactants and the products, and so usually that just means produces or yields because the reactants yield the products. If there's more than one reactant or more than one product, we'll throw a plus sign in between them to indicate that. And if a reaction can go in both directions, like if it's reversible, essentially you're taking the products, and if you can turn them back into the reactants, then you'll see one of those double arrow symbols. After each chemical formula, we'll indicate the phase of matter it's in, so you write either S, L, or G in parentheses to indicate if it's a solid, liquid, or gas, or if it's a solid that's been dissolved in water, we call that aqueous. You will see AQ in parentheses. Not all chemical reactions occur spontaneously. Sometimes they need a specific condition to exist. So if, for example, if they need to be exposed to heat, you'll just see heat written above the yield sign. They might need to be exposed to light, or you might need to run an electric current through them, or maybe some other specific condition. You won't actually see the word other written above the arrow. The actual condition will be written above it. So, for example, some chemical reactions might need a catalyst. So platinum is a common catalyst, so you might see PT, the symbol for platinum, written above the arrow. Or maybe the chemical reaction will only occur if it's at, 3 atmospheres of pressure. So you might see 3 ATM written above the arrow. So those are just some examples you might see. So let's try an example. So for this chemical equation, we've got 2 atoms of solid magnesium. So the chemical symbol for magnesium is Mg. And it's solid, and it's reacting with another chemical, so I'm going to include a plus sign, and it's reacting with 1 molecule of oxygen gas. You don't need to write the 1, it's redundant, so we will write O for oxygen, and oxygen is an example of a diatomic molecule. So anything that's diatomic, it can't just exist as a single atom alone. It's always going to have another atom bonded to it. So oxygen is always just 2 oxygen atoms together. Examples of elements that are diatomic, this sounds silly, but it will help you remember. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. They all need a little 2 after them if they're existing as a pure element, and so you can remember that by Brinkelhoff. So back to this example. Oxygen is in the gas form, and it reacts in the presence of heat. And it's going to be producing 2 molecules of solid magnesium oxide. Remember, magnesium oxide is a ionic compound. So we've got Mg and O. Let's double check those charges, make sure we don't need to crisscross anything. Magnesium's always +2. Oops. And oxygen's always -2. So when those 2's crisscross, they just cancel out. And magnesium oxide is in the solid phase. So that's all you need to write. Sometimes you might be dealing with transition metals that have multiple charges, so you need to include your Roman numerals if you're like writing it out Sometimes you'll see polyatomic ions, so just keep in mind to crisscross your charges or to use prefixes if it's covalent. So moving on from interpreting chemical equations, we're also going to be discussing the law of conservation of matter. It states that matter, and therefore mass, cannot be created or destroyed during a chemical reaction. So in order to follow that law, there needs to be the same number of atoms in the reactant side as the products. So atoms can't just like vanish or appear out of thin air. The reactants, the atoms on that side of the equation are just rearranging to form products. So the same number of atoms on the left need to be the same as the ones on the right, just organized differently. So in order to show that mass has been conserved, we balance chemical equations. So it's the way that we make sure that the atoms are the same on both sides. We can't add or change the subscript, so you can't change those little numbers. The only thing you can do is add coefficients, or like a multiplier in front of the chemical formula. So the example we are going to look at is the synthesis of water. So we've got hydrogen gas and oxygen gas are going to react to form H2O. I am going to draw little symbols to represent these guys. So hydrogen is 2 hydrogen atoms. Oxygen's a little bigger, so I'm going to pick a larger size here. And then we've got our H2O. So you can see there's 2 hydrogens on the left, 2 on the right. Perfect, balanced. If you look at your oxygen, though, there's 2 oxygen atoms on the left and only 1 on the right. So what students will try to do sometimes is change the subscripts, or like throw a 2 on, because they think, okay, now that makes the oxygen balance. Yeah, it does, but you just changed the chemical reaction. Now instead of making water, you're making hydrogen peroxide, which is totally different. So don't do that. What we do instead is we multiply them by a coefficient to make it so they're the same on either side. So what you can do is say that it produces 2 water molecules. So I'm going to draw that out so we can visualize it.
Rose Davis to the main office, please. Rose Davis.
Okay, so now our oxygens are balanced. We've got 2 of those green circles on both sides, or on either side. But our hydrogens are not balanced, so we need to make sure those guys are balanced now. So if we throw a 2 in front of our H2, that's saying that there are 2 hydrogen, or 2 diatomic hydrogen molecules reacting. So now we've got the same number of hydrogen atoms on the left as we do on the right, and the same number of oxygen atoms on the left as we do on the right. You don't need to add 1s in front of the formulas that you don't change. It's just assumed. You just need to write it if it's a number bigger than 1 for a coefficient. Alright, so let's take a look at that example. It's helpful to do an inventory of the atoms that you have before you start balancing the equation. So if you look at this one, you'll see that there's 1 magnesium on the left, 2 oxygens on the left. On the right side, we have 1 magnesium and 1 oxygen. So you can see your magnesiums are balanced, there's 1 on either side, but your oxygens are not balanced. So we can't change the 2 oxygens on the left to 1, but how can we bring the 1 oxygen on the right to 2? So since we currently have 1, if we multiply that by 2 by putting a 2 coefficient in, that makes it so we have 2 oxygens now. It also makes it so we have 2 magnesiums. So we've got to go back to the other side, balance out our magnesiums. What can we multiply that by to bring it to 2? Hopefully you said 2. And that changed your inventory. So now we've got 2 magnesiums on either side, 2 oxygens on either side. We're good to go. You don't need to write a 1 in front of the O2 because it's already balanced, or because you don't need to write a 1 for a coefficient. So this is an example. You're obviously not going to be doing the exit quiz. So what I want you to do is pause this video somewhere on a blank area on your packet or on a piece of scrap paper. Try to balance out this equation on your own. And after you've gotten the answer, go ahead and press play for this video because I'm going to go over the answer. So I want you to check your work. So pause it now, press play to check your work. Hopefully you follow directions and you are ready to check your answers. So first I am going to take an inventory of the atoms that I have. And I'm just going to write them in the same order on the right side just because it'll be easier to keep track. And we've got 1 calcium on the left, and 3 on the right. So we know we're going to have to balance those out. We have 2 fluorines on the left, 1 on the right, 3 sodiums on the left, 1 on the right, 1 phosphorus on the left, 2 on the right. So let's just start out with our calciums. So we can't change our 3 on the right side to 1, but we can change our 1 on the left side to 3. So right now it's 1. If we multiply it by 3, it changes it to 3. So now our calciums are balanced. But we just changed our fluorines too. So because there was initially 2 fluorines to begin with, and you threw a coefficient of 3 in front, you multiplied that 2 by 3, and you got 6. So let's go to the right side. We have 1 fluorine, easy, throw a 6 in front. Now you have 6, and that also changed your sodiums to 6. Back to the left side, you had 3 sodiums to begin with. You got to bring those to 6 now. So if you multiply them by 2, that's now 6. And that changed your phosphoruses to 2, which they were already 2 on the right side. So that's all you need to do to balance that equation. You can put a 1 in front of the calcium phosphide on the end, but you don't need to. You can leave it blank. So that's it. Go ahead and finish up this packet for the practice problems, and you are all set.